All right, so for today's class, we're gonna go over some problems I selected to have like a review for the final tomorrow. Reminder for the final, so it's not on the same time slot that we have the class. It's gonna be between 10 and 1, right? Um, and you're gonna have two and a half hours to solve the whole exam, and the idea is to finish in that time slot between 10 and 1. So around 12:30 you should be submitting your problems. The modality is going to be the same as the midterm, so upload your solutions through Gradescope in a single PDF, so everything will be the same. And hopefully by 1 p.m. everything's gonna be up and ready to grade. In terms of the grading, we will try to do our best with Kate, but probably gonna release the grades by over the weekend or by Monday. Okay. And again, the final is set to be 6 problems, 6 questions. So that's what that's what I've been telling you before. And it's gonna cover all of the topics of the, oh wait, we won't have one problem for each, right? Because then the number doesn't add up, right? But it can span between the first topic of the course until the last one that we covered, which is gravitation. All right. So are there any questions about this, the logistics of the final? All right. So let's move to, yeah. So 6 problems and 6 conceptual questions. That's gonna be the yeah, 6 problems, 6 conceptual questions. Let me just check, but I am pretty sure it was 6 and 6. Yeah, 6 and 6. And each one of them will have a specific point. The conceptual question corresponds to the other 6 problems. Yeah, I tried to have a problem and then right after a conceptual question. So yeah, they're related to the same topic. Yes, Elisa, so 12 in total, but you can think about them as 6 problems, right? With some question about a concept attached to it, right? It's not 12 problems. Yeah. Yes. Some problems are easier and very and they can be solved in a fast way, and the questions are more elaborate. But yeah, it's not 12 problems as in the problem sheets, right? With 2.5 hours, you should be fine to solve them. Of course, I mean the same as we did with the midterm. There's flexibility, so we have an extra half hour in case there is um, a lot of people is not getting to the end, but I think you'll be able to solve it in time. Yes. All right. So let me move to a tablet and we can take a look at some problems. Let me stop this here and share. All right, so the problem we're gonna look first is from set 2 problem problem 5 from the first section of problem sheet 2. So that's motion in one dimension with constant acceleration. Just give you a minute to get there. while I read the problem. Oh yeah, it's motion in one dimension actually. It's the first one. So that's problem 5. It says at 10 a.m. a car starts moving along a straight road at 70 kilometers per hour, and at 12 p.m. another car goes in pursuit at 110 kilometers per hour. So calculate the time and distance from the starting point the second car reaches the first one. Plot the position of the two cars as a function of time on a coordinate system. So the idea here is to get the point where those two cars are occupying the same x coordinate, let's say, right? They have the same position. So let's write down what we know. We have car 1, T01, that's 10 a.m. Car 2, T02, that's 12 p.m. Right, and this one has V1, 70 kilometers per hour, V2, 110 kilometers per hour, right? And we have the initial position of both, which is x1, x01, x02 equals 0. So they are both departing from the same point. They're just shifted in time, right? And we won. We won. T, let's call it asterisk, and x asterisk, where they meet, right? And we want the graph. So this is one, this is the other bullet. Graph x versus t. Right? So we know that these two cars are not accelerating, so they are moving with constant velocity, constant speed. So we can approximate an idea of the graph, right? And then we can put some coordinates to that. Let's see. So we have something like this. We have time in hours. And up here we have position in kilometers. Right? So let's say at time 0, we have car 1. And at time 2 hours, we have the other car. Let me rephrase the slopes there. Of course, this is not in scale or anything, right? Right. So we have something like that. They're encountering at some point in time, which is t asterisk, t star, right? And this is 0, and this is 2. Right, so the car 2 departs 2 hours after car 1. Right? So is there any questions about that idea of the graph? Of course, this is a straight line because there's no acceleration, so the slope of that, the derivative of the position, is going to be the velocity, and the velocity is constant. So we have a linear dependence of time of position with respect of time. Is that okay? Cool. And so this is car 1. and this is car 2, right? And if we look at these, we can say that we can have this portion here as delta x1, which is delta x2, which is delta x, right? Because they're both departing from 0. And if we take a look at this portion here, we have delta t1, which is the delta for car 1, which is t star minus 0. And then we have delta t2, right, which is t star minus 2 in terms of hours, right? So if we write that, we would have delta t2 equal delta t1 minus 2 hours, right? If we are thinking about deltas in terms of deltas of time. And that's is going to let us say that if the speeds are, the velocity are constant, then v1 will be delta x divided by delta t1, right? And v2 is delta x divided by delta t2. So we're calculating, we're just stating the average velocities, which is the same because the velocity is constant. All right. So what we can do is basically write the equations of motion for these two mobiles. So this is x1, and now for t, for any t, let's say we can write the velocity, the speed, 70 kilometers per hour. This is an h per hour times t, and x2 t. So we're using the same variable here, equals 110 kilometers per hour t minus 2 hours. Again, this is to h, that's 2 hours. It's not a variable. All right. So those are the basically the functions that are giving the position with respect of time, right? So this is basically saying that car 2 has 2 hours less to reach the same position, right? Same point. Basically, this is like translating the functions, right? When you get that minus 2 on the t, right? Just imagine as any math exercise, math problem, when you're translating a function, you're pushing it 2 hours. All right. And what we can do here is say, all right, so we need the same position at time t star, right? We call it t star. So we say x1 at t star equals 70 kilometers per hour, t star equals x star, and x2 at t star, which is 110 t star minus 2 hours equals x star, right? So those two are the same. And what we can say, we can do here is just equalize this, right? So we have 70 kilometers per hour, t star equal 110 kilometers per hour, t star plus 220 kilometers, right? I just multiplied, just distributed the 110 over that parenthesis. And so you get 40 kilometers per hour. T equals 220 kilometers. And that's given T star equals 220 kilometers divided by 40 kilometers per hour, right? And that's giving you 5.5, yeah. 5.5 hours. Right? So we have the time at which they encounter each other. Any questions so far? Let me make this nicer. There. All right, good. So in terms of time, it's saying that we are starting this whole thing at 10 a.m. And let's say we add 5.5 hours. So this is gonna happen at 3:30 p.m. That's the time of encounter. 3:30 p.m. And then for the position in which they encounter, we just need to do 5.5 hours times 70 kilometers per hour, which will be 385 kilometers. So that's for the position. So this is up here. 385. And that T is 5.5. Right? So we've gotten those coordinates, and our graph now it's full, it's totally complete. All right, so that's for this problem. Any questions about this one? This is a typical encounter problem. So if those two things are occupying the same, are encountering it means that they are occupying the same position in space. So we need to equalize those functions for the same time, right? And it wouldn't really change. That won't change even if we have acceleration or anything, right? So that's the condition that we need to meet in order to have two things that are being encountered in the same spot in space. All right. Okay. There are no questions. Let's move to another one. Let's look at set 3, section 2, problem 8. Let me find it myself, and you can do so too. All right, so problem 8 says a student wants to determine the coefficients of static friction and kinetic friction between a box and a table. He places the box on the table and gradually lifts the table. When the angle of inclination with the horizontal reaches 30 degrees, the box begins to slide and slides down the table, traveling 4 meters in 4 seconds. What are the coefficients of friction? Right, so this problem has 2 stages, let's say. The exact moment where the kid is pulling up the table and the thing is not it's not slipping, it's not going down. So at that exact point, then we are reaching the maximum static friction, let's say. So the weight is not overcoming that static friction, and this thing is still in equilibrium, static equilibrium. And just an infinitesimal extra angle added to those 30 degrees, the object starts sliding. So that means that we jump to the kinetic regime, right? So we can consider the angle same for both, right? One would be the limit of the static friction, and the other one would be the starting point of the kinetic friction. If you remember that the graph of the friction was like went like up until a specific point there where that the static regime was broken, and then it just went down to the kinetic regime, right? So those 30 degrees are right on the verge of that happening, right? So let's get a sketch of the situation. We have some inclined plane, an object here. This thing has mu static, v0. We have the mass, and we have 30 degrees here. Well, let's call this, let's call this alpha, and alpha equals 30. So I don't get numbers in there. All right, and so we said alpha equals 30. That's the limit of the static friction, right? Free body diagram. So again, this is not the free body diagram, what we have here. That's just the sketch. Free body diagram would mean that we have our axis labeled, right? This, let's do X, Y. Actually, let me be totally strict with this, strict with this. So for the free body diagram, you don't really include axis, right? You just get the forces that are acting here. So we would have normal. Again, it's not wrong, right? But it's not strictly right. The weight, and then we have the friction, which we are calling it friction static. And we can note our system of reference just like this, right? Because that's not part of the free body diagram, although we can include it. It's not wrong. You can do it. And your angle here will be alpha, right? The angle with respect of the rotation of the axis that we are choosing. So we are choosing an x-axis pointing being parallel to the incline, and the y-axis is totally perpendicular, right? So we know that these two are perpendicular, right? Okay, so from that, we know that this thing is in equilibrium, and we can say that the sum of the forces on the x-axis equals F friction, static friction minus and what we can do here is just extend this like what we always do, right? Extend this too, and we have components of the weight. So weight X, weight Y, right? We have those two. The projections, and those are weight sine of alpha for X. So that's going to be 0. and we have Fy equals the normal minus weight cosine of alpha equal to 0. Right? And from this, we can say that the static friction is weight, so weight sine of alpha, and the normal is weight cosine of alpha, right? Again, stating this without saying this means that you're not supporting your statement, right? There is no reason to think that this is happening, that these two things are correct or actually happening if you don't establish that the object is in equilibrium of forces, and there is no, and I mean, you stated that there's no velocity, so this is static, and then you can say this, you can apply Newton's laws. If you don't say this, that you have a 0 here, then this is not being supported, right? So don't jump, even if you know it, don't jump straight to this. State the physics of the problem. All right? Okay. And then we can rewrite our friction as mu static times the normal. That is by definition that we know, so there is no other way to support that. It is what it is. And then we have weight sine of alpha mu static, and the normal we can substitute with weight cosine of alpha. So we have weight cosine of alpha equal weight sine of alpha, and these two are gone. That's why I never wrote mg, right? So we have mu s static equals to the tangent of alpha, and that's around 0.58. Come on. There. So that's the first answer. The static, the mu static. All right. Any questions about that one? Cool. Let's take a look at the second part. So now the kid starts pulling a tiny bit without even changing a degree in that incline. So now the thing starts sliding. So that means that the static friction changed to kinetic friction, and we will have basically the same free body diagram, let's say. So let's say this is for stage 1. And for stage 2, we have, let me draw it real quick. So we have M, and now we have V. This is gonna be going down. We have mu kinetic here. Again, alpha is the same. And it's saying that it went over 4 meters, right? Let me check. Yeah, when the angle inclination with the horizontal, the box begins to slide and slides down the table, traveling 4 meters in 4 seconds. So it says 4 meters in 4 seconds. Okay. And to get the free body diagram, we would get the same thing, but now we have normal. This is Fk, so kinetic friction, and weight. Right. We have all those the same forces with different, let's say, different magnitude for the kinetic friction. And if we write the net forces for x, that's gonna be Fk, sorry, Fk minus P sine of alpha, and this is gonna be equal to mass times acceleration. Because now we know that this thing is sliding down, so it's gonna start from velocities from a zero speed, let's say, and it will start accelerating because there's not a balance between Fk and the x component of the weight. So the x component of the weight hasn't changed at all, but the friction has. It has changed. So as it changed, it's smaller, right? So that would mean that this operation here is it's not possible to be zero. Sorry, I got P here. Just let me know if I put P instead of weight of W. So that means that there's gonna be an actual value of that net force, and we know that from Newton's second law, that's m times the acceleration. All right. So if we work this expression here, we will just let me write first the other one. Fy n weight cosine of alpha equals 0. And from here we get that the normal is, like before, weight cosine of alpha. And if we put this in here, then we get mu c kinetic, sorry, mu k, mu kinetic, weight cosine of alpha minus weight sine of alpha equals mass times acceleration, right? So I just substituted the expression for the kinetic friction. And if you work with that, now we can write mu k mg cosine of alpha minus mg sine of alpha equal ma. And m's are going away. And we finally get mu k g cosine of alpha minus g sine of alpha equals a. And we know this a is going to be negative because it's pointing down, right? The thing is accelerating against the x-axis that we established before, right? All right, so we have the acceleration, but we need to get this right here, the kinetic coefficient. And so what we can do is take what the problem is saying, that this thing is traveling 4 meters in 4 seconds. So if we just establish this problem as just a straight line motion with constant acceleration, which we have calculated right here, then we can apply those equations, right? So the final position is going to be initial position plus initial speed t plus 1/2 of the acceleration t squared. But we have x initial, we can call it 0, right where the block starts moving. V initial is going to be 0 because it's at rest at first. And then x final, it's 4 meters minus 4 meters, right? Because it's going against the x-axis, it's going down, and t is going to be 4 seconds. All right, so we can say that these terms are going away, and then we get x final equal 1/2 of the acceleration, which is mu k g cosine of alpha minus g sine of alpha, right? So that's the acceleration of our motion. It's right here. Okay, and this is gonna be t squared up here. Any questions about that? we're just applying straight line motion with a constant acceleration, and the constant acceleration is dependent of the gravity and the coefficient of kinetic friction. And of course the angle, right? But we know those. We know gravity, we know the angle. All right, good. And this is gonna, if we just work this expression, it's gonna have, you're gonna have 2x final divided by t squared. And that's, oh, yeah, let me, yeah, this mu k g cosine of alpha minus g sine of alpha. And this is giving us 2x of t squared plus g sine. So I'm getting the sine part to the x side. Alpha equals mu k g cosine of alpha. So I'm isolating the mu k. And then you can do 2xf plus g sine of alpha divided by t squared. All of that divided by g cosine of alpha, right? G cosine of alpha. And that's equal to mu k. And if you calculate that, then you'll have 0.52. Okay. You have all the data to calculate this. So this is 4 meters. And t is 4 seconds, right? G 9.8, alpha 30 degrees. G, we know 9.8. Right? Is the value of G negative in this problem, or was the negative sign included in the previous steps? So that's a good question. It's really important to note that G is never negative. G is just 9.8. What defines the negative sign is your system of reference. So never attach a sign to G. Your sign's gonna be the sign of you know the of what you're doing. It's taken into account here, right? So let me see here. So you just got the minus sign there, minus weight. So you're putting the minus of G, saying that it's gonna is going against your system of reference, right? There's no need to add a minus on the actual value of G. G is always 9.8. Okay. Hope it's clear. And again, even though we say that, you know, we say that acceleration is going to go against here, it's going down, so it's going against x. That's already taken into account in this expression, in this calculation. So you don't need to put a minus here, right? You don't need to put a minus in your equation here. Sorry, here, right? So that's already taken into account into the expression of your of the whole problem, right? When you're choosing the system of reference. And I mean, that's the easiest and best way to do it, right? The signs will always come on their own if you're consistent and if you're following your own your own establishment of the system of reference. Okay. All right, any other questions about this one? Now let's move to the next one. All right. Cool. Let's go to set 4, problem 20. Oops. Right. So work and energy, right? So it's a block of mass m equal 5 kilograms slides down a frictionless inclined plane. Ramp. Ramp. It's charged from a height h equal 9 meters, and the ramp is inclined 25 degrees above the horizontal. Calculate its initial potential energy after it has traveled 0.5 meters, and then calculate its kinetic energy when it has traveled 4.5 meters and when it is 4.5 meters above the ground. So those two are different. Those two things are different, right? And let me start, and then we can take a look at C, so we don't lose the idea of the first questions. Again, we have an incline. Let me try to make it bigger. There. We have an object here. Let's call it M. And we have, it's saying that it's going down that ramp. This is H, big H equal to 9 meters. This thing is 5 kilograms. And it's saying calculate the initial potential energy after it has traveled 4.5 meters. So if it traveled 4.5 meters, means that it went from one point here to another point here. And the coordinates of those 2 points, it's 4.5 meters. It's not saying that it went down 4.5 meters. It just traveled along the incline for 4.5 meters. And if you do that, then of course you can calculate this, let's call it small h, which will be calculated from the angle, right? Because we know that this is 25 degrees, right? So small h would be 4.5 meters sine of 25. So that's 1.9. Right? So the change in the, let's say we have the y-axis pointing, up, right? And x down there, x here. So in the change in the y position, it's 1.9 meters when it's going down the ramp 4.5 meters. Let's call this point. Actually, the first one is going to be A, and this other point is going to be B, right? So remember, when you're working with energies, always compare, always be strict with the points that you're looking at, right? With the comparisons that you're making. So you'll be able to fully support your answer, right? So for A, it's saying determine that initial potential energy after it traveled 4.5 meters. So the we were using U, right? Yeah. So UGA, it's mg big H, right? So that's the potential energy, gravitational potential energy at point A, and that's gonna be 5 kilograms, 9.8 meters per second square, and 9 meters. That's 441 joules. All right, that's fairly straightforward. That's the gravitational potential energy for A, because we know the total height in which the this is a block. Yeah, the block is positioned, right? And then we need to calculate that energy after it traveled 4.5 meters. So what we're doing here is calculating UG for point B, and that would be mg big H minus 1.9. Right? So H minus, let's put this, H minus small h, because we know we want the actual height for point B, right? So do not confuse it with just a small h, right? So the y coordinate of B is going to be big H minus small h, okay? And that is G 9 minus 1.9, and that's 347.9 joules. Okay, so that's the gravitational potential energy for point B after it traveled 4.5 meters along the ramp. All right, any questions about that? Any doubts? Right, cool. So this is a part A. Let's take a look at part B. Part B. So for part B, it's saying calculate its kinetic energy when it has traveled 4.5 meters and when it is 4.5 meters above the ground. So those two are totally different things, right? So after traveling those 4.5 meters, that's asking for the kinetic energy for point B, right? And that would be 1/2 of the mass VB squared, basically. But what we can say here is that we don't have any kind of external input to the system. There's no dissipative force acting here, so we can say that the total mechanical energy is being conserved, right? So we have delta mechanical energy equal to 0. There is no work of external forces. All right, so we can say external, sorry, no work of dissipative forces, right? Non-conservative forces. So we can say that the gravitational potential energy of A plus the kinetic energy of A equals the gravitational potential energy of B plus the kinetic energy of point B. But we know that this one is 0, so we just cancel it. And we have that we want the kinetic energy in B, so kinetic energy in B is going to be UGA minus UGB, right? I'm just solving for, sorry, I got a P here, UGA, right? Yeah, I'm solving for K for the kinetic energy, and that's 441 joules minus 347.9 joules, which is given 93.1 joules. And there we have it. That's the kinetic energy for point B. Right. Notice that we haven't had need to calculate the velocity there, although we can, right? We can totally calculate it now. But that's basically, I mean, it makes sense, right? It's the change, it's the change of the gravitational potential energy, right? So you started with some gravitational, some potential energy of at point A, and then that energy needs to have gone somewhere, and it went to make the block move. So it increased the kinetic energy. So the difference, it's the kinetic energy that the block gained from A to B, right? But this is fundamental, right? So we need to establish that. We need to establish that there is no change in the total mechanical energy of the system. So we need to, we are able to state this, right? Because this is going to be EB and this is EA. So the total mechanical energy at point A and at point B are the same. Sorry, this looks awful. A. All right. And then it's asking, let's see, it's asking, so that's for when it traveled 4.5 meters, meaning that we are at point B. And the other question is when it is 4.5 meters above the ground. So 4.5 meters above the ground, it's a totally different point, which is, let's say, somewhere over here. And let's call that C. So that's 4.5 meters this high, 4.5 meters above the ground. And of course, the mechanics is the problem solving is basically the same. So we are comparing now point C with point A. And we don't need to compare it with point B actually, because we can just skip that intermediate step. So we can say that the potential energy for point C is equal to plus, right, plus the kinetic energy of point C is equal to the potential energy point A plus kinetic energy of point A. Again, we know this one is 0, and we just end up with, we just solve for A for KC, which is UGA minus UGC, and that's 441 joules minus mg 4.5 meters. Because now this is the actual height that we are taking into account. H, the height at point C. And that's 220.5 joules. This problem is basically to practice the fact that the height of the object is not the distance that it went through in the ramp, and to get to get accustomed to get the actual points that you're comparing, state the points that you're comparing the energies for, right? So this will be E, the total energy at C, and the total energy at point A, right? And again, delta E equals 0, so those two are equal, and then you can state this that you have down here. Then you can say this. Then you can say that the kinetic energy equals the subtraction of those two quantities. It's not the kinetic energy, actually, it's just this. This is the definition, right? So if you just omit this whole reasoning and you just get this Kc equal to that, not even writing this, then it's meaningless, right? Cool. Let's continue then. So it has more questions. So now it says, if there is now a kinetic friction, so attention, we have a dissipative force. If there is now a kinetic friction with mu equal to 0.15, then from what height should the block be dropped so it takes the same time to reach the ground as in the case without friction? Let's take a look at that. part C. So if we have mu kinetic, because it's gonna be moving, 1.15. Then we say we need to calculate the time it takes to reach the ground without friction, right? Because we want to match that, and we want to get the height. So we are able to match the time to reach the ground as if it had no friction at all. So let's see, C1. So we say no friction. No friction. So we have the velocity or the speed. We were talking about the modulus. So speed, we know that it's pointing down. So speed equal to 0. The acceleration on the x-axis would be g sine of 25, right? Are we all good with that? Do I need to write get the Newton's second law? So the only component would be the weight. The weight's pointing down, so g sine of 25. That's the modulus of the acceleration. And then distance, the actual d would be d sine of 25, and that would be h, right? So we want to calculate the full distance between point A and let's call it point, let's say D. Yeah, so the bottom is D. So that D distance, the small d is the distance between A and D, so the whole ramp. And from this, we can say that D is h divided by the sine of 25 degrees, right? So we know that, we know the distance that it needs to go through. Let me get the free body diagram just to have a complete. So, and I'm just including the axis here. So careful with this because we establish x. Now we're establishing, let's establish x pointing down. So we get all positive. So we get all positive components here. You know, the object is moving down, so let's put it down. This is weight. Then we would have normal. And that's all we have there because there is no friction. So we can say that we can actually calculate the x of t, that in this case would be 1/2 of the acceleration t squared, right? Because we don't have any initial position, we don't have initial speed, and that if we get that for the final t, let's say, let's call it t final, x for t final, when it reaches point, oh, let's call it D, right? When it reaches point D, so the end of the ramp, that would be h over sine of 25, which is the distance that it's going through. And this is 1/2 g sine of 25 t squared. All right. So this is straight line motion with some constant acceleration, no initial speed, no initial displacement. We're taking the 0 at where the block is starting to move at point A, let's say. Any questions about this one? About this? All right. So t, we can get t from here, which is fairly straightforward. Just do the math there. And that's the square root of all that. That's All right, the calculation is 3.2. Again, if you go checking the numbers with me, I'll appreciate, but I think that's what I got. So that's 3.2 seconds. So that's with no friction at all. Okay. And if we add some friction now, so we have friction, we have mu c equals, well, I'm writing it again, but just to state that we are at mu k, sorry, we are at the kinetic regime of friction, then our free body diagram is going to change because it's going to add 1/4 there. So we have this normal weight, and now we have a friction. So it's Fk, right? And now the sum of the forces on the x-axis is going to have the component of the weight x, right? Which is going to be mg sine of 25 minus the calculation of the friction that we know that, I mean, we've just done this, so let me make it faster. So n is going to be mg cosine 25. So the kinetic friction is going to be mu k mg cosine of 25. I'm just being more compact here, right? Because we just did it on the last exercise. And so we get minus mu k mg cosine of 25 equals m acceleration on the x-axis. And we can take the m's out, masses going away. And now we get some expression for the acceleration, which is the same as we calculated in the previous one. Sine of 25 minus mu cosine of 25 equals the acceleration for the x-axis. And now we can write the distance. You know, we can write our equation, right? With the time. So we want to go through a distance d in the same time as it would be going when it had no friction. So we just input that time for our position on the, so let's say we have x of td, that would be the distance that we are calculating, d, so that's 1/2 of the acceleration, and x, so that's g sine of 25 minus mu cosine of 25, 3.2 seconds squared, and that's giving d equal 14.38 meters. So if that's the distance, then we need to calculate the height, right? So let's call it h prime, and that would be d sine of 25. That's 6.08 meters from ground. So we need to throw it at 6.8 meters from the ground in order to reach D at the same time as it wouldn't have any friction. All right. Questions about this one? So it is clear what we've done here. So we calculated the time it would take to get to the ground to point D with no friction at all. That's 3.2 seconds. And then we've calculated the function that defines the position as if it has friction, which is this one that we have here. And then we calculated the distance that it will that it would need to cover to span those with those 3.2 seconds, right? And that distance is 14.38. And then we calculated the height with that distance that it would go through the ramp, which is 6.08. Okay. Let's go to the last question for this one. So part 2 says, from what height should the block be dropped so that it reaches the ground with the same speed now? So you want to reach the floor with the same speed as in the case without friction. So same logics here. We need to calculate the speed with no friction. So no mu. We know. Let me just be really, because we're running out of time. Let me just be just say that the potential energy, the initial one, it's equal to 1/2 of mv final square. So that's mu at point A, and this is kinetic energy at point D, right? If there's no friction, these two are not, there are no distributive forces, and the total mechanical energy will conserve, and all the gravitational potential energy will be transformed into kinetic energy. And so we can calculate the final velocity, which is 2gh, and you can recognize this from the free fall, right? It's the same speed that you get on a free fall. 13.28 meters per second. So we know that. And now we want to get, if we have friction, let's say now we have mu k. We can state that the variation of the mechanical energy of the system is equal to 0, right? So there is work of conservative forces, right? So we want to make the same comparison, but now we need to take that into account. And for that, we would say that the work, again, this is work, not the weight, work of the friction force, let's put it this way, would be equal to the variation of the total mechanical energy, right? And that's equal, if we are comparing final points or with the initial points, so A and D, we can say that the gravitational, let's start with the kinetic energy at point D minus the kinetic energy at point A plus the potential energy at point D minus the potential energy at point A, right? That's the variation of that total mechanical energy, which is the work of the friction. And we know that this one is 0 at A, and we know that this one is 0 at D, right? And we would get 1/2 mv final squared minus mg h. Let's call it, I've run out of h. Let's call it just h. because we know that we're calculating that height, that specific height. So we want that. And now the work of the friction is gonna be minus friction Fk. The distance, because the friction is against the movement, it's parallel to the displacement. So basically we get a minus there when we do the dot product between the vectors, and that's 1/2 m b final squared minus m g h. Okay, and we can just substitute with the expression for the friction. So for that we have mu mg cosine of 25 h sine of 25 equals 1/2 mv final squared minus mg h. Is that clear how we are calculating the distance travel and the friction? So the height divided by sine of 25. Okay, hopefully there's no confusion with that. And let me rephrase this. So we want to get h out of this, and we have the final velocity calculated from before, because we want to match this velocity, right? We want to match this speed right here. So let me get h. So this be mgh minus mu mg cosine 25 h sine of 25 1/2 m v final. Let's get rid of the m's. Actually, I could have done that before. Let's get rid of the m's, and we have put h here, so we can just divide everything by the term minus mu g over tangent 25, because we have cosine over sine, equals 1/2 v final squared. And now I can get h in terms of this whole thing, just yeah, divide h equal v final squared divided by 2 over that whole term, which is g minus mu. Oh, sorry, I omitted the k, but you know that it's the only mu we have, right? Mu k g divided by tangent of 25. And that's, if you calculate that, just putting the value for the final velocity, the final speed that we calculated before up here. So we have all that, g, we have mu k, tangent of 25, okay, and that's gonna give 13.26 meters. Oddly similar to the speed, right? But you know, it is what it is. So that's the height that you're gonna need to throw this object from in order to get to the same speed at the end of the ramp. 13.26 meters. All right, and it makes sense, right? It would need more, because before we were throwing it from a 9 meters high. So, sorry, 9 meters high, and it yeah, sorry about the graph here, but it looks like the 9 meters is just the green part. The 9 meters is this whole part. Hopefully you didn't get confused with that, right? So this is that the whole bar. So you need to throw it from a higher point, because you now this thing is slowing down, right? Okay. So you have dissipative energy. So you need to add more. Let's say you need to add, you know, in quoting, add potential energy. So you get more kinetic energy. You get the same kinetic energy in the end. So you get the same final speed, and you can take into account what's depleted by the dissipative force, which is the friction, right? Any questions about this one? It's kind of big to put it in just one. Well, yeah, it's not even letting me. Well, barely. All right. But hopefully you got it. Any questions? All right. And that's what I got here for today. So hopefully we would have reviewed some of the stuff that was covered in the midterm, and I just didn't want to go over the same problems that we were going through class last week, so you can get like a refresh of the first half of the course, let's say. And then you go over. Well, so is there no questions? Can I stop the? I'll stop sharing for the tablet. And today you're gonna go over with Kate through some other problems, and those would work as practice too, of course. Let me stop the recording because we are over time now.